All right, so in this video, we're going to be looking at autonomous differential equations. We're going to be looking at a comparison between direction fields, phase planes, and phase lines, all of which can be used to represent the behavior of these autonomous differential equations. Now, recall that autonomous differential equations are equations that involve the function and the derivative of the function, but do not explicitly involve the variable that underlies the function. So in this example, time is our underlying variable, but there is no variable t in the differential equation, only in the derivative notation. So that means that the slope of our field, the slope of our direction field, does not depend on time. It only depends on the position in the y variable, in the function variable. Now, this is a common type of expression that we might have for a population model. We can see from our direction field that we've plotted here, that we have an equilibrium position here at 6, which comes from our factor in our expression y minus 6. This is a typical carrying capacity situation where we have the slope increasing up to the carrying capacity, the slope decreasing on the other side of the carrying capacity. So this is a stable solution. On the other end, we have from the 2 minus y factor, we have a equilibrium at 2. This is a threshold because you need to be above that to grow. And below that, you basically think of it as an extinction line. If you fall below that, the negative slopes will drive you to 0, which is, of course, itself its own equilibrium. So the 1/10 here is simply as a scaling factor so that we can see the slopes more easily. They're a little too vertical or a little too flat if we don't include the scaling factor. Again, it's just for visualizations. And the 2 minus y is a way of concealing a negative sign that's actually in the equation. We could easily write this negative 1/10 y times y minus 2 times y minus 6. But putting it through the parentheses makes it just a little bit more compact. So this is a common way of expressing a population model that has both an threshold, extinction line, and a carrying capacity. Now, if you study this direction field, you can see that at any point on the graph, if you pick a value for y and you go all the way across the graph, the slope is exactly the same everywhere because it only depends on how high it is from that y equals 0 line. That's the only information that you need in order to plot this. So autonomous direction fields are often problems that are given very easily on exams because you only have to plot a certain number of values, and then you know that like all the way across you can fill in your direction field because it's always the same as you go across. Moreover, you only have sign changes on your direction field where you cross an equilibrium. So it's very easy to plot where's my slope equal to 0. It's going to be a horizontal line, and those are my equilibria, and the sign of the slope can only change when you cross over those equilibrium positions. So an even easier way of plotting a direction field is simply to acknowledge those sign changes and those slopes. So for example, here is our equilibrium at y equals 6. This is stable. Just going to mark it with an ST. This is y equals 2. We're going to mark this with an unstable. And then, of course, y equals 0 is our other equilibrium. Again, these are the only places that the slope can change. So you'll notice that above this y equals 6 line, the slopes are all pointing toward that stable equilibrium. Between y equals 2 and y equals 6, all the slopes are pointing upward at various slope levels because you will get flatter as you approach the equilibrium and steeper in the middle. But basically, they're all going upward. And likewise, in the between the y equals 0 and y equals 2 line, they're all pointing downwards. And then we could complete the graph. You'll notice, even though population models don't really go below 0, we can see that we have positive slopes here below this. So one way of translating this is you can have a reduced direction field that simply plots your equilibrium values like so. And again, because we know what the behavior has to be from the sort of full blown out direction field, the main pieces of information that we need are which direction are the slopes pointing. And so we can extract that information basically from a sign chart of our direction field to determine which regions have a positive slope, which regions have a negative slope. And then that actually gives us all the information we need. From that point, since we know the graphs are going to stabilize at each point, we don't necessarily need to know the individual slope values because we know that in between equilibria, our equations are going to look largely S-shaped. It's just a question of, are they increasing or decreasing? And outside all of our equilibria, they're essentially going to look exponential, either decaying or, in case negatives mean anything, increasing up to that threshold. So some negative, some reflected exponential. Again, these ones in the middle here are often thought of as logistic function-like, although the equation is obviously more complicated when you have multiple equilibria like this and not just two. But the behavior is largely similar. You have some S-shaped curve that's very steep in the middle or as steep as possible and then flattens out as it nears its upper and lower bounds. Now, we can translate this information into an even simpler representation by looking at the phase line. Now, the phase line essentially takes our direction field, takes this information that we have in 2 dimensions, and reduces it to a single dimension. So, for example, we might draw a line like so, and then mark on it our equilibria position. So here is 0, and here is 2, and here is 6. So these are our sign changing directions. And then what we represent on the phase line is simply the direction of the slope. So is it positive or is it negative? And we do that with arrows directly on the line. So for example, if the slope is negative, then all of the values are going toward the equilibrium line at 6, and so we put a downward arrow on it. If the slopes are positive, we put an upward arrow on it, and again, that indicates we can see that the stable equilibrium at 6, all the values are getting sucked into it. In between y equals 2 and y equals 0, we have a downward slope. So again, they're pulling away from this unstable equilibrium at 2. And then for completeness, the upward slope below 0, again, it says that 0 is a stable equilibrium. Everything goes there if you're in this range of values. So this is a phase line that is distinct from a phase plane, which we're going to talk about in a second. Now, the phase line is essentially, again, just a one-dimensional representation of this two-dimensional simplified direction field. Now, you want to be careful about when you're using a phase line, if your professor is asking for a direction field or a phase plane, and you draw a phase line, that's not exactly what they were asking for. So it's important to keep all of these things distinct from each other. Now, as far as the phase plane goes, the phase plane is another way of representing this differential equation. And essentially what we do is we create a graph like so, where the direction field, the differential equation, is our y-axis, and the horizontal axis is the function variable. And what we're looking for is essentially to plot this as a function, as if it were a function of x, so to speak. We have zeros at 0, 2, and 6. And then we can create a sign chart since our function is already factored. If I put in a value which is like 1, I'm going to get a 1 here, which is positive. This whole coefficient outside is positive. And then 2 minus 1, that's going to be positive. And then 1 minus 6, that's going to be negative. That's going to give me a negative value down here. If I plug in a value that is negative, like say -1, then I'm going to get a negative out here. 2 minus a negative is going to give me a positive. And then a negative minus 6 is going to give me another negative. That's 2 negatives. So that'll be positive. If I continue plugging in points, something between 2 and 6, I'm going to get a positive, and then I'm going to get a negative. So what would this look like graphically if this was like just a graph of a polynomial? Well, it's essentially going to come through like this, come back through like this, come back through like this, and so forth. So again, one thing that you can do is you can use technology. You can plot your polynomial function, let's say in x, on your calculator. You'll get this curve, and then you can use it in reverse to identify what the signs of the slopes are. So this phase plane is going to tell you that, oh, on this side of the graph, for values that have y less than 0, that's going to be positive because the curve is above the x-axis. Here, between 0 and 2, the curve is below the x-axis, so that's going to give us negative values for the slope. Here, we flip the sign again. That'll be positive values for the slope. And then when we go back past 6 again, we'll return to negative values of the slope. From the phase plane, you can then use that information to plot on your direction field which direction the signs are going. So below 0, you're going to get a positive. That's our upward pointing arrow. From 0 to 2, you have a negative. So that is the downward facing arrow. Between 2 and 6, we have a positive again. So that will be our upward facing arrow. And then for values that are greater than 6, it flips over and goes downward again. Now, sometimes it can be a little confusing because you're reading one graph representing the differential equation in one format, and everything is on its side, relatively speaking, in the direction field. It's very easy to like read left to right on this graph and accidentally read, instead of bottom to top to bottom, and get the signs backwards. But this is another way of thinking about how to construct a simplified direction field rather than filling out points, plotting a whole bunch of points to fill this in with a great deal of detail. Autonomous direction fields make it easy for you in that you basically just need to know where the equilibria are, where the zeros are, and then the direction that the arrows are pointing in. So these are 3 different ways of representing the behavior of your autonomous differential equation, or 4 if you count the simplification here. We have direction fields, our simplified direction field, our phase line, and our phase plane. So on exams, I usually personally will ask students for either the direction field or the phase plane, but there are certainly professors who will ask about phase lines. And again, it's really important. If I ask for a direction field, I don't want a phase line or a phase plane. So even though these all represent the same information, it's important to give the information that you're being asked for. But these are all going to, again, give some sort of information holistically about the behavior of your differential equation when there is no explicit dependency for time.